All right, what we have is a series of models that we'll look at. And I think that you've seen these already, but just to make sure it's really clear as we're going forward, what exactly we're taking a look at and how they work, I think will be helpful. So this all comes from the idea of having exponential growth or an exponential growth model, which is relatively simple in the fact that the change in the, let's say, population P over time T, that change is proportional to however much population there already is. So if you have a small population, you'll have small growth. If you have a large population, you'll have large growth. And K is just a sort of constant of proportionality. So the growth rate may be larger or smaller depending on various factors such as, food and just general fertility and that sort of thing. Now, what that leads to is if you already have a positive population, your growth will initially be somewhat meager, and then it will sort of take off over time. And let's say if you start at a different starting population, it'll look like so, and kind of so on and so forth. So these are a few different exponential growth curves depending on where you might start with the initial population. If you start with no population, since we're taking K times P, K times 0 would be 0. So if you had no population, you would just remain at no population, which makes sense. That's what we would want. Now, this is not a very realistic model in most cases because there's going to be some limit to what the environment can sustain as far as a population, the limit in food or space or what have you. So what a better model is, just pretty much across the board when we're talking about any kind of population growth or exponential growth that would eventually be limited, is to say, take the same model here. And now notice I've written it down here with one exception. The only exception is there are these parentheses. And what we're going to do is we're going to enter some expression so that it's exponential when the population is low, and then it changes so that it will level off and it won't just grow off to infinity like it does in the exponential case. The right expression to do that would be something like this, taking 1 minus, let's say, population times C, where we'll let C be the carrying capacity. And as an example, let's take that C and put it, let's say, here. Now, if you think about this just in terms of, let's say, numerics, if you look at the case where P is very small, P over C is pretty small. So you just have 1. Let me admit some people. You just have 1 times K times P. So when P is really small, this term disappears and you essentially recover the exponential growth model. Then when P is really large, let's say, when it's close to C, then you have roughly 1 minus 1. So you have 0. That means that this whole value, because it's Kp times, let's say, 0, that's going to be relatively small. So the growth is going to slow down as you near C. It's going to be large when it's going to be relatively close to the exponential growth model when P is small, and then the growth is going to be small itself when the population approaches C. Curves would look like this. So if you had population curves, which I'll draw in cyan here, they might start out looking like exponential growth, but then as you approach C, you get this inflection and they do something like this. Or it again may look something kind of like so. Moreover, if you start above the carrying capacity, Since P over C will be larger than 1, then you'll have a negative slope. So it'll look something kind of like this. And again, if you were to start with 0 population, it would be just like the exponential case where you have 0 here. So the exponential one was sort of unsatisfying in the way that it didn't really model population growth well, because in the real world, in every case, there's going to be some sort of upper limit. We've modeled that here. Now, what we'll be doing today is taking this logistic growth model, this one down here, and we'll be looking at variants of it. So we'll take logistic growth, which, let me just fill this in real quick. 1 minus P over the carrying capacity in each case. Then, in the case of constant harvesting, what we're going to do is we're going to constantly subtract an amount H. That's constant, so H will be some fixed number. Then for the proportional harvesting model, what we'll be doing is subtracting, let's see, yeah, they use E times P, where E is some, let's say, positive real number. So what we'll be doing is taking logistic growth model, we'll be adding these two respective terms, and then investigating what happens in each case. So that's the goal of the lab. And the way to motivate this is to imagine, let's say you had a fishery and you were taking away a certain amount of fish each time. You know, you're letting this sort of population grow as it would in, you know, whatever stream or what have you, where you're going to harvest the fish from. And then every so often, you're going to take away a certain amount of fish, you know, for selling or what have you. And it's going to be the same no matter what the population is. That would be constant harvesting. That the amount you take away never changes. You're always going to take away, let's say, 500 fish a week or something. In the proportional case, you might say something like, I'm going to take away 1% of the population. So if the population, it's 100 fish, you'll take away 1 fish. If it's 200 fish, you'll take away 2 fish. So it only, it depends on what the population is at the moment. So constant, you don't look at the population, or proportional, you do look at the population and take a proportion. All right, those are the models we're going to look at. So let's go ahead and jump into the applet. So I will not have the questions on screen. I have that on a separate screen that I'll be looking at and reading off of, but we'll now look at the applet. So let me stop sharing this screen and reshare this. Okay, you should see now a harvesting model, population versus time applet. In this particular case, we're going to be working with a rate of 0.18. So if you ignore this part that I've highlighted, if you ignore that part in the teal greenish color, it's just exponential growth. So it grows at this rate of 0.18 or 18%. Because of the logistic growth that we're modeling, there's this carrying capacity of 50,000. And currently, we're not doing anything to it beyond the basic logistic growth. Excuse me. So we're not taking away any additional fish. We're not doing any harvesting. That's why this is 0. And now let's go ahead and jump into it. So I'm going to look at the instructions really quick. Okay. So for the first thing that we want to find out with this model is the stable equilibrium. What that is, it would be, let me get the annotation. We would like to find some constant harvesting value so that what we would get would be something like this. Oh, I'm trying to draw a straight line across, but you know, the mouse is hard. So we want to get something like that. What we don't want to get, so that would be good. Actually, let me put that in a different color. So we want to get something like this. That would be good. What we don't want to have happen is we don't want something like this. We don't want it to like go down like that. That would be bad, because what's going to happen is you're going to be harvesting at a constant rate, but eventually you'll deplete your source of fish. And we don't want to have something like this, because what that means is we could have been harvesting more fish. So we want to harvest as many fish as possible such that we maintain the population. That if we harvested any more fish, it would drop below. It would like eventually crash the population, and any more would eventually stabilize, meaning we could have had more. So right now, what I'll let you do, and you can sort of private chat if you've got questions, but just spend some time experimenting with different values of constant harvesting. Notice what I did there. I took away 100, and then it showed this graph here, which means there was more fish I could have harvested. Find the most number of fish that you could possibly harvest while having an equilibrium, just a straight line like the green line. So take a few minutes to try that out. And again, feel free to private chat me if you've got questions, and I'll be happy to answer. So take about another minute to see what you come up with, and then we'll talk about it further. Okay. So I may have misspoke earlier. I think I may have called the line like this one the stable equilibrium. And if I did, I apologize. I actually can't remember offhand. But this green line, if it was straight, would actually not be a stable equilibrium. It would be unstable, because we notice that the solution curves move away from it. Actually, no, never mind. Ignore what I just said. Yeah, let me clarify some confusion that I was having, and maybe some of yours. So what we like to do is find an equilibrium value. We'd like to get a line just like the green line, like this. And for a second, I was looking at these other curves and thinking that they moved away, but that's not really how we want to look at it. We want to imagine curves that have different starting values, let's say below like this or above like this. If the curves that had different starting values would approach this green equilibrium, then this would be a stable equilibrium. And I think it is, but let's see. So what we want to do now to investigate whether this equilibrium is stable, because these other curves actually don't tell us whether it's stable or unstable. And to actually find out exactly what this green curve is. So right now, what we've been doing is kind of guessing that, oh, maybe it's like 1400, or maybe it's 2300 or whatever. But we're just kind of taking some guesses at what the equilibrium is. Now we'd like to use some algebra to find out exactly what it is, and then we can check there to see whether it's actually stable. So let's do that. Let me erase some of this, and then we'll graph a dp dt versus p curve. Now, what we'd like to do is, let's see, I'm going to highlight this. So we want to take this function down here, dp dt, and we want to think of it like here. That's not a great color. We want to think of it like here is the quote unquote y value, or the dependent variable. Oh, that's just horrible to look at. Okay. The orange is going to be the dependent variable. And then we're going to have, let's say, what color do I want to use? Maybe purple. Purple is going to be the independent variable, which is p. So now we're going to graph that. What that will look like, actually, I know what I can do. So let's go to Desmos. And let's clear the annotations. So let's now take this function dp dt, and that will be our vertical axis, the dp dt. The horizontal axis will just be p. So we'll take this thing right here, and then let's see, actually, hold on a second. I want to enter h, but how are we going to do that in Desmos? Let's just try something in particular. Let's try like a given value, like 1400. And this should be, let's say, y equals. And let's see what we get. Okay, we get something like this. So if we graph this thing, what we get is two equilibrium. We get an equilibrium at 10,000 and then at 40,000. But correspondingly, if we change the constant harvesting to, let's say, I don't know, 1,500, we get something like this, and so on. So we can see what the curve of this looks like. Now let me double check here. So to find, oh, okay, yeah, thanks. Someone mentioned the slider. Good. Thank you for that. Add slider for H. Nice. And can we not increase it? Yeah, thank you for that. Let's say it's as much as 50,000, and we'll do steps by, I don't know, 50 maybe. Let's do 10. And then as low as 0. Good. And good. All right, cool. So we can see how changing H will change the graph here. So if we have H be, let's say, too big, it will make it so that the population just crashes right away. Like if we do 5,300 and we go back here and we type in 5,300 and graph the population, we can see it just crashes right away. And if we do something like 1,400, we see that it kind of stabilizes. I think you can do more than 1,400, but just as an example, it looks maybe something like that. All right, now what we would like to find is what? Sorry, I'm looking at the lab instructions. So what we want to do is find the stable equilibrium in terms of H. So this gives us a notion of what this looks like for different H, but what we want to do is come up with a formula involving H. So we know that we can vary H and we get these different curves here, but we want to know what is going to be the stable equilibrium based on H here. So which would be the stable equilibrium? If we remember from last time, what we want is ones that are below the line. We want the slopes to be positive. So let me annotate just to remind us. If we take, let's say, another graph here, and we went like this, where this is P and this is T. If we now look at, let's say, 1,400, or I'm sorry, 40,000. So here's 40,000, 1, 2, 3. And we look at that line like this. We know it's stable because here the slope should be 0. And the slopes below that or just below that will be positive because we see that the function is positive. And then the function is negative when we move to the right. So that means the slopes look like this. So 40,000 would be our stable equilibrium. But of course, as we change H, that equilibrium, stable equilibrium will change. So what we want to do is find it in terms of H. So in order to do that, what we can do is just use some algebra, essentially. So I'll set that up, and then I'll let you work for a second. But what we're doing is we're going to say, oh, I can't write this well. Let me jump back to where I can actually write. So I'm going to change the screen share. Let's change it to this. So we have this model, this 0.18 p times 1 minus p over 50,000, where 50,000, if I didn't clarify before, is the carrying capacity. So we know this is some downward facing parabola. It's going to look something like this. And we want to find this point here. That's going to be our stable equilibrium. But it's going to vary depending on h. So we take and we say, let this be equal to 0. And now once we do that, we let it be equal to 0 to find where it hits the p-axis. We go through, and I think we get something that looks like this: negative 0.18 over 50,000 times p squared plus 0.18 p, and then just minus h. And now you, if you like, you can do a little bit of algebraic manipulation. You can multiply by 50,000 over negative 0.18. And if you do, what we'll get, I think, is p squared, let's see, minus 50,000 and p plus 50,000 over 0.18 times h. Now at this point, you can think of this as 0 is equal to a p squared plus b p plus c, just in the usual way we looked at quadratic equations. And now you can use the quadratic formula. So I'll leave you to try that out. And as usual, feel free to type in chat if you want to double check your result. But that's what we want to do now. And notice your answer, p is equal to blah, 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 will have an h involved in it. So that's what we're doing. We're finding the equilibrium in terms of h. And someone asked a question, so I'm going to give some further clarification. There's two lines that we're looking at. Or two graphs that we're looking at, dp dt versus p. And that gives us this curve here, which I'm going to color. And then there's another graph, which is p versus t. This is exactly the same idea as the autonomous equations lab. And this point here in yellow is exactly this line here, or will give us this line here. And what we're doing is finding that that is a stable equilibrium, because we'll have sort of arrows like this from there being positivity over here. And then there'll be arrows like this from the negativity here. So what we're trying to find is this equilibrium value by looking at this as a quadratic equation, solving through and finding out what p should be in terms of h. And what that amounts to is giving us this equilibrium solution. So we're finding the equilibrium solution by finding the value where this curve intersects the p-axis right here. So take another, let's say, minute to see if you can't find out what P should be. Okay. Now, what should happen if you use the quadratic formula with the appropriate values is you're going to think of A, in this case, as being equal to 1. So A should be equal to 1. B should be equal to negative 50,000. And C should be equal to 50,000 divided by 0.18 times H. Using the quadratic formula, that's going to be negative B over 2A plus or minus 1 over 2A times square root of B squared minus 4AC. The B squared minus 4AC, we can see, is going to look something, actually, I'll leave it. I don't want to totally give it away. But we can see that this will involve H, right? Because it's going to have C. It's going to be 50,000 divided by 0.18 times H. So C will involve H. In order for this to make any sense, we want to make sure that this thing is greater than 0. Otherwise, we're taking square root of a negative number, which means there won't be any intersection in the real plane that we would see up here. So if this graph was completely below, then that would amount to this number being less than 0, because that would mean there's no real roots. So we want this to be greater than 0 if we're going to find an actual real root like this. So one thing you want to do is take this B squared minus 4AC in your version where you actually have it filled in with the different values, and you want to make sure that that is greater than or equal to 0. So that's one condition. Then call that the first condition. The second condition is you want H to be as large as possible. So there's two conditions. One, you want to make sure this number here, again, it'll be filled in with different values based on what you entered. That should be greater than or equal to 0. And then also, you want to make sure H is as large as possible because we want to harvest as much as possible. When you get a number, it should look roughly like the number that you guessed at the beginning of the lab. So go ahead, take a little bit to experiment with that, maybe 2-ish minutes, and feel free to private chat me. You should get an H that's somewhat similar to the one you guessed at the beginning of the lab. So someone asked, are we solving for H? Yeah. You want to try to find what this lowercase h is. You want it to be as large as possible under this condition. So take about another minute to see what you come up with. And again, feel free to private chat if you're curious whether that value seems to make sense. Okay, let's jump back to the actual applet and see how it compares to what we found. So now let me jump back to this. And we'll jump over here. So now let me clear these curves. If we started out with, let's say, harvesting 0, the population is going to approach the carrying capacity, 50,000. If we, let's say, did around 1,400, then what that would do, or maybe even 1,450, is it would level out the population so there would be no change. If we take something like, let's say, 2,200, it goes like this. Now, it's hard to see here. That's why we went through the whole process algebraically, because it can be hard to tell from the graph, but it looks like it may sort of level out. That is, there is some spot, let me get this up. There's some line where it sort of asymptotically approaches that line. That's supposed to be a straight horizontal line, but of course, mouse issues. It looks like if we tried something larger than that, let's say 24, let's do 2,500, make sure it's clear. Then 2,500, it will crash the population. 2,400, I think, will still crash the population. So the goal would be to get there to be a stabilization where you can harvest as much as possible, but it doesn't crash the population. And I think, let's say 2,300, I think would still be too much. We can see that there's this kind of negative slope and it's kind of continually going down, or it seems to. But again, it might be hard to tell even here whether 2,300 is good. But algebraically, if you went through all these steps successfully, you'll find a value somewhat around 2,300 such that you get this leveling off, which I'll draw in an annotation. It'll essentially kind of level off like that, where it asymptotically approaches some equilibrium value. And that value we found based on this H down here. It's not 2,300. 2,300 is too much. That was just the last one I put in, but it's some H value. Okay. Now, this was the process for constant harvesting. And if this process made sense, it's really no different for proportional. So for example, with proportional, what we do is we, down here, instead of putting a constant value, we take a rate, and I'm seeing if they start a rate. We take something like 0.1 times p, or lowercase p, I guess. And now we graph. Now, 0.1 times p means you're taking 1/10 of the population at any given interval. And actually, this looks pretty good. Hopefully, I didn't just exactly guess it right away. But if you were to take something like 5% of the population and compare that, that would look like this. If you were to take, let's say, no percent of the population, of course, that's going to be this. And you can see 1% of the population will give this. So you're taking some percentage of the population. If you, took 20% of the population, I think that's going to crash pretty quick. Yep, it does. So you're experimenting with this proportionality, this percentage of the population. And what you want to do is first investigate graphically, though I think I already gave you the right value. Investigate graphically to get a curve kind of like this one I'm highlighting in purple, where it'll reduce down but then stabilize. And you want the proportionality to be, of course, as large as possible because you want to try to get as much possible from the population when you harvest. Then after that, what you want to do, so after you guess a good value, though 0.1 looks pretty good. After you guess that, you'll want to go ahead and then go through the algebraic process. So what that means is that you'll then take this thing, and instead of having an H from before, what we'll do is we'll have an E. So now you can imagine going to Desmos back here, and instead of having H, you can have, let's say, capital E, which I'll add a slider for, times P. Lowercase p, I guess. And then that E should be in a range of 0 up to 1, let's say in steps of like 0.01. And as you change that E, where's my slider now? There we go. You see you get kind of something like this, where it sort of rotates around here. I'm a little surprised by this. But at any rate, it's the same kind of deal that you can imagine seeing how it looks. Oh, that's because of the scale. Seeing how it looks with different E values. And then what you want to do is actually solve for P, the equilibrium solutions in terms of E. So now I'm going to jump back to where I'm writing. But again, this is exactly the same process we did for the constant harvesting. So back here with the constant harvesting, we took this and we said, okay, set it equal to 0. That is the way we find the different equilibrium values and then equilibrium solutions. Now we're going to, in a similar manner, set 0.18 p times 1 minus p over 50,000 minus e. So maybe I'll put e here in magenta, e times p. And we want to set that equal to 0. So now when you rearrange it, do the algebra, you get something like this. P squared, let's see, plus 0.18p minus p times e. And if you do a little bit more algebra, you'll find that you get this plus 0.18 minus e times p. And now you can actually factor this. I don't even think you have to use quadratic formula. You can factor this to find out what the different p values are that would give you no change in slope, or that's what it means to set it equal to 0. This is just what we did in the last lab. And then you want to find that e to be as large as you possibly can. So you want to maximize that e value. And then that's essentially the idea for the lab. Then when you look at the lab report, it tells you how to sort of structure this information, but that's largely it. We do the investigation via the applet. Then we set up the formula and find out what the exact value is to maximize our harvesting, either constantly harvesting or proportionally harvesting. Excuse me. So with that, I think that's all I've got for today. You're welcome to stick around and ask questions for a few minutes, but if not, have a good day. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.